ladies and gentlemen, tonight's speaker is Mark Bailey. Mark Bailey, MRIA, served as director of Armagh Observatory from 1995 to 2016, and has researched interests ranging from small bodies of the solar system to extragalactic astronomy, including aspects of local history and the history of astronomy. Minor Planet 4050 was named Me Bailey for his work on the origins of comets, and he was awarded an MBE for services to astronomy in 2007. So can we give a big Mexborough and Swinton Astronomical Society welcome to Mark Bailey? Welcome, Mark.
Thank you all. So I'll start off then, and I just want to check, are you seeing the slide properly?
Yes.
Okay, well, thank you very much for your invitation to speak. As Paul said, I'm retired director at Armagh. I was in post for nearly 21 years, and I'm very happy to be retired, I have to say, away from all the admin and bureaucracy that there is associated with anything these days that touches government. But I'm now able to consider some of the things I used to do in astronomy, and also enjoy giving the occasional talk. And I apologize if there are little glitches in this presentation, but that's only due to lack of practice with Zoom, and as you've experienced already. So the talk is about near-Earth objects, and I'll cover a review of their origins and the effect of their impacts, and then finish off with a number of slides describing the way that we assess risk these days. And you'll no doubt understand and recognize that this can be applied also to the risk of pandemic, which we're all living through also. Okay, and then I'm happy to take questions either during the talk or at the end. I don't know how you do that. Probably at the end is best. So away we go. All I've got to do is work out how to move the slide. Oh, here we go. Don't want to go too far. Sorry. Okay, I've worked out how to do that too. So the first slide asks the question, what are near-Earth objects? And the emphasis is on objects because there are two kinds. One class is asteroids, and the other would be comets, and then the third class, I suppose you would say, could be called asteroids or comets, in other words, dead or inert, devolatilized comets, and then fragments thereof. And the sizes range from that of houses, a few meters up to tens of meters, up to that of mountains, typically tens of kilometers, and then ranging right up to the size of a small country, maybe 100 kilometers or more. And so these are objects which have been discovered in the last few hundred years, 200 years, and they have been discovered most recently in ever increasing frequency owing to the new sky surveys that have been operating since I suppose, the late 1980s and thereabouts. So this slide illustrates the growth in knowledge of near-Earth asteroids. The first one, as I say, the first asteroid was discovered in 1801. In fact, supposedly on the first night of the 19th century. It was later called Ceres, and very soon after came Pallas, Juno, and Vesta. So I suppose those after Ceres, they thought this was the missing planet between Mars and Jupiter, and illustrated in that little box there on the right. But after the other three were found, they realized they better call them minor planets, and that name stuck, along with another name later, which was the name asteroid, something looking like a star, but not a star because it moved. And you can see from this list how rapidly those objects numbers have grown. There was nearly a century before they discovered the first Earth approaching asteroid. But then 1932, the first Earth crosser. And this was quite exciting because it showed that some objects other than asteroids, other than the classical asteroids, if you like, the ones occupying the space between Mars and Jupiter principally, those objects are, I suppose, a few of them anyway, on orbits that were much more unstable, lasting much less than the age of the solar system and potentially planet colliding. And by 1970, there were 30 of those objects known, and by 1990, around about 100 or so. In the following decade, there were 900, and by today, there are now 26,000 objects on Earth crossing orbits known. It doesn't mean to say that there have been any increase in their numbers, it's just that the numbers known have grown dramatically. And this is still a small proportion of all the known asteroids, which are numbering about 1 million nowadays. So it's a fantastic job to keep track, if you like, of these objects and update all their orbits and identify the new ones when they're discovered. As will become clear, the total population of near-Earth objects of a size liable to be significant in terms of the survival, if you like, of civilization, bigger than about 1 kilometer, is around about 1,000. There was a figure recently suggesting about 920 compared with 890 known as of middle of this year. The collision probability of these objects is very, very small. So something like 5 parts in a billion per object per year. But with that number of objects known, that means that no doubt there will be 1 or 2 small impacts. Most of these are small objects. And the mean collision frequency of the larger objects, ones bigger than 1 kilometer or so, is around about 1 object per 200,000 years. So in a sense, at this point, we can all relax and just look at these objects in the sky, knowing, if you like, that we'd be very unlucky. Now, what happened there? Knowing that we'd be very unlucky that one were to be colliding with Earth in our lifetime, or even that of our child's lifetime. Sorry about this. I want to start this movie off, but every time I click on it, it seems to, let's see if I can get it to go, sorry. Oh, here we go. Yeah, so this shows the growth, and it's a movie made by our former computer manager and a student, Scott Manley, who you might know the name of. He has he's quite famous on the internet these days. And the green ones are ordinary asteroids, near Earth, not near Earth ones, but ordinary ones. And you can see as we zoom in, showing just the inner planets now, you can see, look out for the beginning of anything that looks like it's approaching the Earth, the 1932 first Earth crosser, and then the other ones in red denoting those that are the other ones that are discovering with time. So basically you can see at a glance with this little movie how rapidly our knowledge of the space between the planets has grown, and how rapidly even our knowledge of the small objects that are on planet crossing orbits has grown. So I'll just let that run, it won't go on much longer. So that brings you up to about year 2000 or so, or thereabouts. And you'll notice that there are little clusters of objects around planet Earth, and then almost like Trojans here, separated from Earth by 60 degrees or something like that. Okay, what about their sizes? I've said already that some of these objects are large, but the majority are very small. And the size distribution is often modeled. Obviously, it's brightness that you see. So you have to convert from brightness to size, usually by assumption. And you often model these things by what are called power laws. So in this equation, the numbers with a size bigger than diameter d is proportional to d to some inverse power law. In other words, the numbers decrease with size quite rapidly. For small objects, the index is 2 or thereabouts. For medium-sized ones, I'm sorry about that. For medium-sized ones, it's 3.5 for 10 to 70 meter diameter objects, which includes the size of the Tunguska object. In other words, there are lots more smaller objects than size 70, and there are much bigger than that. And then for the vast bulk of the range of observed objects, this index is approximately 2, and that covers most of the what we would call the impact hazard. The much bigger objects, bigger than a few kilometers across, for near-Earth objects, they fall off very steeply in numbers. And that's just telling you basically that there are very few known very large objects in the present Earth-crossing population. So roughly an inverse square law applies over the whole of the relevant range for the impact hazard. And I note at the bottom that the largest craters on Earth, because those are produced by impacts, require objects with diameters bigger than 10 kilometers, of which there are none in the sample currently Earth crossing. So it just shows you that that's very rare. And maybe they're not asteroids at all. Maybe they're fragments of comets. So the next slide shows what these things look like, and there's some images of comets and asteroids. Most of the things we're looking at are like this satellite of Ida. But looking at the comets, it's interesting to note that there are round ones like these two, Wild and Temple, and then there are comets which like Borrelli and Halley and others that look more, how can I put it, more like a bowling pin or something. So as if they're made up by the collision, by the aggregation of two components, or maybe more than that, or maybe they've evolved into that shape owing to sublimation. So the different types, different sizes. There's no intermediate cases as far as I'm aware, but you might know some. You might know better than me. Let's look at some comets. What's famous about comets is that they were originally feared by humans, and there's a long story of mythology and myths and other stories relating to how comets in the sky were always associated with doom and disaster. And the reason for that I'll come to at the end, hopefully. This is an engraving of Comet Donati, which appeared in 1858, and it brightened in the summer of that year to become an easy naked eye object, and it was described by many at that time as the most beautiful comet of all. Another famous one is Halley, of course, which some of you probably remember seeing. And if you didn't remember seeing it, you'll be lucky enough to see it again. Very few people see it twice in their lives, owing to its period of 75 to 76 years. This image from the Royal Observatory Edinburgh Schmidt telescopes shows a famous disconnection event in the gas tail. And it shows rather nicely, can you see the cursor? I hope you can. It shows very nicely the the smooth structure of the dust tail as compared with the, very fine structure and striated structure of the gas tail. And the last picture shows the Halley's Comet as it was imaged by the Giotto spacecraft all those years ago. This one shows another famous comet, which I'm sure most of you will remember seeing, Hale-Bopp. And this shows the observatory at Armagh, and the dust, can you see the dust tail and the blue gas tail in that image, which I took simply by holding an ordinary camera and exposing a 35mm camera in those days and exposing it for about 20 seconds or so. And it's signed by Thomas Bopp. You'll see that picture. He visited the observatory in 1997. We're all sorry to hear that he died. I think it was earlier this year or the end of last year. And the other thing notable about this picture, can you see the observatory ghost just here? I don't know if can you see where the cursor is pointing?
Yes, in the
can you see the man behind? Well, you can see the shutters are closed. So what this man's doing behind the shutter and still being visible is a mystery. Well, sort of. So that's the observatory ghost. Every good observatory must have a ghost. Okay. Well, now we're talking about comets. We have to talk also about their end states. And they are very fragile objects, actually. There are some that look just like they're breaking up in the ordinary Earth's atmosphere, as it were. Of course, the interplanetary medium is very empty, almost like a vacuum. And so they're just breaking up by whatever, probably the sublimation effects of outgassing. It's almost as if you take a handful, don't recommend doing this, but take a handful of cigarette ash or something and throw it, you get the same impression of something just breaking up in space. That's one kind of disintegration mode. Another is what you might call just normal outgassing, where here's an example in the middle. And then there's this third kind, which is historically been associated with some of the brightest comets visible, is the collision of comets with the sun. And those sun-grazing comets can become very bright owing to their proximity to the sun, when the very large amount of heat from the sun landing on them, and therefore excessive amount of radiation. A fourth disintegration mode, a fourth disintegration mode is a similar mode to the sun grazers, but in this case, collision with planets. And the one that we're mostly aware of is the comet Shoemaker-Levy 9 example, where it was discovered that there was a strange shape in the sky not far from Jupiter. And it turned out that this comet was, had previously passed very, very close to the surface of the planet and had been broken up by the tidal stresses of that close approach. And it was not just, it wasn't orbiting the sun, it was orbiting the planet itself. So it came around 2 years later, and it was on an orbit such that it was destined to collide with the planet, and it produced all those impacts and impact scars on the planet. And you probably noticed from a recent, the astronomer, at least I saw it, there was an astronomical telegram, that I think it was a week ago that they recorded a flash on Jupiter. So it'd be interesting enough to look hard at Jupiter just to see whether there are any impact scars that anybody can discern, albeit a week later. So I suppose the reason for having this slide particularly is that it highlights the uncertainty that anybody has in making predictions. And that uncertainty arises because we don't understand or don't know necessarily the orbits of these objects in Earth crossing or planet crossing orbits. Had somebody asked anyone who knew anything about it, how often do things collide with Jupiter? And they were speaking before 1993, they would have said on average once every 2,000 years. And yet not so long after that, there were 20 impacts in the space of a week. And the reason for that is that the comet that caused those impacts, the progenitor, was orbiting Jupiter, and then it broke up in its passage close to Jupiter and produced a trail, almost like a debris stream of material, all the fragments of which were destined to collide. So if you have the same circumstance affecting the sun, as you do with the sun grazers, or affecting the Earth, a comet fragmentation event producing a debris stream that was intersecting Earth's orbit, then you would have a much greater chance of impacts. And that's, of course, what we recognize these days as meteor streams, the meteoroids running into the Earth every year at a particular time of the year. But that might occur also with larger objects. It just depends on the circumstance. So comets are more interesting in a sense than asteroids because they're less known about them. Very briefly, there are two main classes, the long period and the short period ones. And the short period ones divide themselves into two classes, which I will refer to as Halley types and Jupiter family comets. The Halley types come from all over the sky and may well themselves dominantly come from the Oort cloud. Excuse me, I'll take a drink. The Jupiter family ones, on the other hand, are coming from a variety of other sources, principally centaurs. And the centaurs represent a stage in the evolution of comets from beyond Pluto, the Edgeworth-Kuiper belt population, which has a number of subpopulations. And these objects can become planet crossing and ultimately end up falling onto Earth crossing orbits or subjovian orbits, I should say, and therefore becoming typical Jupiter family comets. And the point to make here is that all comets are fragile, and they typically survive in near Earth space anyway for timescales less than 200 or 1,000 revolutions. In other words, a few thousand to maybe a few tens of thousands of years. And therefore, this is a population which is time variable in terms of human lifetimes and the timescale of civilization. So the disintegration of the largest members of the population must be taken into account if we're going to understand the evolutioning total of the interplanetary complex. And the comet size distribution, similarly to the asteroids, is modeled by power laws. And we typically assume something like a cumulative size distribution proportional to the diameter to the -2, up to a diameter of about 50 kilometers. And then something similar to what happened with the asteroids or the near-Earth asteroids happens. And there's a sharp fall off for the much bigger objects. Although there are bigger objects in the outer solar system, as you all know, Chiron is a famous example, the first such comet stroke asteroid to have been discovered. And this is in an orbit which has a perihelion close to Saturn and is on a trajectory, if you like. I don't mean but in a line sense, but in an average sense, and in a sense in which most clones of Chiron will end up evolving into Jupiter family orbits. And I note at the bottom of this slide that a comet with a diameter of the order of 5 kilometers runs into Earth roughly every 10 to 100 million years. This slide's included just because it shows the time evolution of a typical, well, maybe not atypical, but an example of a clone of Chirons. And this was some time ago, this work was done about 1990. And we computed the evolution of 100 Chirons, in other words, varying their orbits ever so slightly to see what would happen both forwards and backwards. And here's an example of a Chiron which 75,000 years ago became Earth crossing, the dotted line. There's the Earth's orbit is about there, and also short period. So in this case, if it were the real object, you could argue that there was an object 75,000 years ago with a size of order 100 kilometers or more on an Earth crossing short period orbit. And that you would understand, I'm sure, would be a very significant object in the sky. But this is just one example. The more important point to make is, however, that the majority of clones of Chiron displayed this sort of behavior. And so you can probably say about Chiron that it has previously been a short period comet, and it's not coming in for the first time, with a probability of about 90% of being true. And that's similar stories can be made about other among the centaurs. And so the story of the centaurs is very interesting. Not only do they provide ground truth, if I can put it that way, of very large objects in the solar system that must from time to time become Earth crossing, but they also illustrate how it's possible that our ancestors, thousands or tens of thousands of years ago, might even have been witness to one such event. Okay, so let's look at the effects of impacts. In short, why should we be worried about them? Why? Well, I suppose we shouldn't really worry, but why should we be concerned about their effects? If they're small objects, size of Tunguska or slightly bigger, they produce craters potentially up to a kilometer across. They impact with energies up to about 100 megatons, which is a huge amount of energy, comparable with the biggest nuclear weapon ever made. But that's at the small end. That's at the small scale of asteroid impacts. If the diameters are bigger, from 100 meters up to 500 meters, then the energies are correspondingly bigger, and the impacts could destroy a large city or a small state, and oceanic impacts will produce massive tsunami. And once you get to larger impacts than half a kilometer, or maybe up to 2, the energies are sufficient, whether they land on the land or on the ocean, to have a global effect. So in terms of the risk, if you're looking at small objects, the risks are low, the impacts and their effects are big, but they're localized. But if the sizes become bigger than half a kilometer up to 2 kilometers, and of course nobody knows quite what the boundary is, the effect is going to be global, and therefore it doesn't matter where on Earth it hits, it's going to cause an effect that is very significant. And bigger objects, 10 kilometers or larger, produce the potential for large craters. In outline, you can imagine multiplying the diameter of the object by a power of 10 or so to get the size of the crater, and the global mass extinctions will flow from such impacts. Now, see if I can get this slide to move forward. Yes, okay. Here we have a nice graphic produced by a man called David Rajmon, if that's how it's pronounced. And here you can see a lot of impact craters, most of them below the ground, a lot of them anyway, and just showing, if you like, that the Earth is indeed a bombarded planet. And there are large ones and small ones. There are confirmed ones and there are probable ones and all the rest. And the numbers grow from year to year as the geologists and geophysicists identify more and more such craters. Now, a large impact, as I said, can produce a mass extinction of species. And this happened 65 million years ago when the canonical 10-kilometer asteroid ran into Earth and wiped out or finished wiping out the dinosaurs. And this changed the course of evolution of life. So without that, you can be reasonably sure that we wouldn't be here today, simply because of the chaotic nature of evolution. And the fact that if you rerun the tape, or rewind and rerun it, then you get a totally different outcome. A bit like so many of those films, Sliding Doors, for example. I'm sure you've seen that at some point in your lives. So then, how do we estimate, or how do we discuss the risk that these objects in space pose, not just to the Earth itself, though that's probably a negligible effect, a bit like a gnat hitting your car windscreen, but more to the people who live on the Earth, ourselves and other life forms? Well, the risk is the word that we use, and it's the chance that something bad will happen in common parlance. But in fact, risk is the product of two quantities. One is the event itself, whatever it is, and then the other is the frequency. So you could get the same risk from a very frequent event that had almost no effect, as compared with a very infrequent event that had some effect. So it's the product of those two things. And different people quantified risk in different ways. Not sure, did I do two? No, that's okay. So here's a slightly more precise definition. It's the chance of loss or injury, or the degree of probability of loss, probably still too loose. And then the Oxford English Dictionary, the possibility that something unpleasant will happen. And then the Treasury, some years ago, 2004, probably still the same. Risk is uncertainty in outcome, whether positive or negative. And of course, you can have a positive outturn from some event as well as a negative one. So the Treasury would like to look at risk from both angles. And then there are, I suppose there's the question then of relatively unpleasant events, and how common are they? And here's what I call natural catastrophes. I have a slide here showing the San Francisco earthquake, the 1953 flood on the East Coast and over the Netherlands, famous 1980 volcano, and of course the 2004 tsunami. And the point about these catastrophes is that they're sudden, and they often happen with no warning or very little warning. They have a high impact, but that impact is always local, and they're short-lived. In other words, if you survive it, you're okay. And they're relatively common or frequent in this sense, which means that there are enough of them that we can begin to assess their nature and study them and learn more and more about them. So that's what I call natural catastrophes. The next slide shows the less common, what you might call natural catastrophes. And these can be distinguished because they're neither sudden nor short-lived. Sometimes there's a slow-acting process. In other words, if you can read the runes, there's plenty of warning. They may still have a global reach. And the one that is in the news at the moment, of course, is climate change. So although you might argue which country contributes most to the climate change, doesn't matter, because we're all affected in some way, although how we're affected depends on where you live on the globe, probably. And then there's no recent example or experience, and so very little scientific knowledge of the object, of the situation or the circumstance. We can't really be sure in our scientific predictions. And so what tends to happen is that we adopt a subjective response, either to denial or fatalism or some other human response. Maybe we just ignore the science, or maybe we follow it blindly, who knows. And then but the point really is there's greater scientific uncertainty, however you look at these natural natural catastrophes, simply owing to lack of knowledge and the need always to extrapolate, which is not a good idea, but to extrapolate from our current best theories, our best understanding. And how do we capture this kind of risk? Well, as you know from everything that's gone on in the last couple of years, you need interdisciplinary studies. These studies might combine historical investigations as well as scientific modeling. And as Rumsfeld is most famous for, we must be alert to the unknown unknowns. In other words, we must avoid groupthink, because who knows what's around the corner. Okay, well, this can be viewed graphically, and the UK is famous for having its risk register. And here's a diagram from the National Risk Register with no quantitative coordinates. On the right is frequency, and going up and down is relative impact. And there lies pandemic human disease, quite frequent and quite high impact. But nowhere does it show asteroid impacts. You've got floods, you've got attacks, you've got severe weather, all the other things we're familiar with. But the unfamiliar, of course, doesn't show, because how can it? We don't know where to put it on this diagram, even though there's no labeled axes on it anyway. Well, the Health and Safety Executive had a good approach, or have a good approach, in my view. A man called Nigel Holloway, who worked with us many years ago, presented this diagram, or something like it, at the Space Guard meeting held at the Royal Greenwich Observatory in Cambridge in 1997. And his figure was adapted from the Health and Safety Executive's figure, tolerability of risk, which goes back to 1992. And the point here is that you plot the number of fatalities on a logarithmic scale versus the mean time interval between events. So here you have an interval of 100, 1,000, 10,000, 100,000, a million years. In other words, high frequency at the top, low frequency at the bottom. And here you have deaths, 10, 100, 1,000, 10,000. In other words, going to the right, 10 million over here. And these are very, very severe risks, events, if they were to happen. So you can then divide this diagram up into the intolerable regime and the tolerable regime. And in between, you do a cost-benefit analysis to knock the risk down as low as reasonably practicable. And at that point, you can all argue what's reasonable and what's practical. But the point is that at some point, it becomes a waste of time trying to live in a perfect cotton wool existence where there are no risks. And on the other hand, if you identify a frequent but highly damaging event, then you want it not to happen. Okay, so this is what's known as the ALARP principle. It's connected to some degree with the precautionary principle, although the latter is something which you have to be a wee bit careful about, I think. Otherwise, you may run the risk of not doing anything. So let's look at the effects of impacts again. The diameters, small ones, you might think, therefore, are perfectly acceptable. Think of Tunguska. It had an energy of the order of 10 megatons, and it landed in the middle of Siberia. And the only effect, as far as we were concerned, was bright nights. So you were able to play cricket at night, in the middle of June, admittedly, and you were able to read a newspaper, so it's reported. So you might think that's something we won't worry about, unless you happen to land, or it lands on your head, sort of thing. The next one is larger objects, as we mentioned, craters up to 5 kilometers. And then maybe those would be more concerning, particularly if you could predict where and when it might happen. If it was a half a kilometer size object and it was going to land on the island of Ireland, you might wish to remove yourself and go on holiday in Spain or something for the duration, and then come back home and pick up the pieces. If the diameter were bigger than that, then, as I mentioned before, it doesn't really matter very much where it hits the Earth. It's going to have a global reach, and that we've seen that already in examples of tsunamis, albeit those produced by earthquakes. And then larger objects running into Earth, you have huge craters, massive climate change, and global mass extinctions, or massive environmental change, I should say. Okay, well, impacts also do occur, so let's not try and imagine that it never happens. The Tunguska one I mentioned a few times. Sikhote Alin was another example in February 1947. And here's an example of a smaller object, though I think I'm right in saying it was an iron asteroid, a meteorite, and therefore quite a localized event, though very impressive at the time. And then there's a picture here done by J. Tate, Tunguska over London. So imagining that the Tunguska event had come in from the southeast and just smack over London, and then everything inside the M25 basically would have been flattened, and therefore a very huge, very large local effect. But probably you'd be all right in Yorkshire. Who knows? You'd probably have your windows blown out, perhaps. So let's have a look at an actuarial approach to estimating the cost of impacts. And this is an insurance approach. The insurance premium, or the amount that you or I should be prepared to pay by way of taxes, if the government had a long enough view, it should at least cover the insured losses. In other words, the collision rate times the cost of, on average, of one near-Earth asteroid collision for a globally devastating impact. So as I mentioned before, the impact frequency is roughly 1 per couple of 100,000 years. If you assume a quarter of the population dies, which would be 15 million people, and if you follow convention and say, well, a single UK life is worth about £1 million or so, 1.5 million, then for the UK alone, the cost works out to be 100 million a year. And your question then is, should we multiply that up for the whole world? Is every single life worth the same amount? All the rest of it. And whose job is it? Is it our job to clean up the asteroids for the whole world? Or is it someone else's job? And if the latter, then we should be having meetings to assess who pays the most to get the job done. And large impacts, on the other hand, occur so rarely that we're probably safe to ignore them for the next 10 or 20 years, long enough that we can pass the buck on to our children. So we have to think of the long view. And one way of doing that is to consider civilization as a life form or as an organism with a lifespan of 10,000 years. And then these infrequent events, in that sense, become more frequent. So for some reason it went the wrong way. Sorry about this. Okay, so we go back to the FN diagram, and now we'll put asteroids in. And you can see where they lie. They're way out in the intolerable region. They run into the Earth about every 200,000 years, and they have tens of millions of people dying for the UK alone. And Nigel put it very succinctly. He said, speaking from the health and safety direction, if NEOs were a business, they wouldn't be allowed to operate. In other words, they're far out in this intolerable regime. It's a bit like nuclear power. That's what level do you try to protect society from the worst possible events that a power station might produce. Well, now let's look again at comets. Comets have orbits that are much harder to predict than asteroids, owing principally to their friability, their ability to break up, and also the fact of their sublimation, which can deflect them slightly in orbit from time to time. So it's always worth checking a comet's orbit and improving it, correcting for the so-called non-gravitational forces on their orbits. They also, as we mentioned, contribute to the near-Earth object population, and they produce meteoroid streams and debris, which we know cross Earth's orbit. And here's a couple of examples. This is probably an asteroid, but who knows, running a fragment of something running into the Earth. I think it was, it says August the 18th, 1783. Here's another one which you'll recognize probably as the Leonid shower. And the Leonid meteors, as was shown by a colleague, David Asher, that the meteor trails produced by the comet at different passages, this comes around every 33 years, they are very finely concentrated for a few orbits at least in space. So finely that it's like the Earth going through a bowling ground where it may or may not go through the trail. And that was what made the Leonids such a puzzle until David Asher and his colleagues had managed to work out how to make the predictions. And now we're very familiar with the idea of predicting meteor storms or meteor outbursts and so on, owing to ability to predict the trails of particle debris emitted from comets at particular perihelion passages. And so in this case, the 1833 trail was passing around there and very close, therefore, to Earth's orbit. Here's the Earth rolling around its orbit, the 13th, 14th, and 15th of November. Other advances in cometary science includes, as I mentioned earlier, the size distribution includes large bodies. So had you been reading the subject, say in the 1970s, people would have been very reluctant indeed to acknowledge that some comets had diameters bigger than, say, 10 or 20 kilometers. And earlier than that, they didn't even understand what comets were made of. You remember the Littleton dust ball hypothesis compared to the Whipple icy nucleus picture. So it's relatively recently that we've acknowledged that giant comets, in my terms, diameters bigger than 100 kilometers exist in both the long and short period comet flux. We also recognize the evolution of the orbits is highly chaotic, a bit like the weather, and therefore highly unpredictable in the long term, owing both to outgassing, possible fragmentation of the comet itself, and mostly owing to the close approaches of comets to planets. And you don't have to come very close to a planet for the orbit to be deflected in a fairly unpredictable way. And the comets are also very fragile, as I keep mentioning, and the examples of the sun grazers, the Shoemaker-Levy 9 effect, and this results in them having relatively short physical lifetimes. And this evolution of comets leads to streams or trails of debris in the solar system. In other words, they don't have to hit a planet to have an impact because their debris can have the requisite impact on Earth. And the effects of impact, some are shown here. Well, you've got the canonical impact that led to the death of the dinosaurs, an asteroid with the size of the scale height of the atmosphere punching through the atmosphere. So the front end, as it were, hits the ground before the back end has gone through most of the atmosphere even. You've got Sikhote-Alin, and you've got at the ground zero of the Tunguska event, a totem pole erected by the scientists who visit it most years. And they have developed a mythology. They don't believe a word of it, but the mythology is that the totem pole is dedicated to Akpi, is the fire god, the Siberian god of fire who brings fire to the forest. And the mythology is that you've got to go and pay homage to Akpi and leave something that's valuable to yourself at his feet. And this is Tunguska in 1908. So you can see the things that people have left, bus tickets and coins, an axe, and all the rest of it. And so there you see actually the burgeoning of religion. I'm not saying that anyone really believes this, but all I'm saying is it illustrates by example how it is that people such as myself might make a pilgrimage thousands of kilometers to this point, simply which was marked simply by a major event, a small asteroid impact. So there's something to reflect on. And then let's look at the medium-term implications. Well, human evolution has gone on for thousands, hundreds of thousands, and perhaps millions of years. And on a million-year timescale, we can expect of the order of 5 Earth-impacting kilometer-size near-Earth asteroids, 10 Jupiter giant family comets with diameters bigger than 100 kilometers, 20 Halley-type giant comets, 2,500 long-period giant comets, and 10,000 Earth-impacting Tunguskas. And there's various evidence for this, some of which I just note here. First of all, there's a very unusual comet, Comet Encke, in a very short period orbit. There's the sun-grazing families, asteroids and comets. And there's the meteoroid stream associated with the Taurid shower, which is in turn associated with Encke. And I ask the question, can this be used? The obsession of ancient societies with celestial events, going back, in this case, deliberately back one slide, to the mythology associated with impacts. How would our ancestors have responded to a Tunguska impact close to them or within, as it were, shouting distance of their tribe? Okay, well, here I expand on this slightly. Ancient societies obsessed by the sky. There's the early astronomical interest, the megalithic monuments, Stonehenge, Newgrange, all the rest of it, Orkney, and prehistoric rock art, some of which is shown here. A historian called Nugabier explains that ancient astrology can be much better compared with weather prediction from phenomena observed in the sky than with astrology in the modern sense of the word. In other words, what he's suggesting is that the ancients were observing the sky, they were predicting the weather, they were predicting the meteors, they're predicting the passage of the moon, the movable planets and all the rest of it. And they were doing it in a untutored way, but nevertheless still scientific, making connections and correlations and the rest of it. And this obsession that they had with the sky is consistent, doesn't prove it, but is consistent with there being more activity in the sky in the past. And that suggests that some solar system phenomena may change on much shorter timescales than we normally consider possible. And that's where I would bring in Donald Rumsfeld's point. We have to be avoiding groupthink. And sometimes in science, you have to suspend your disbelief in order to develop a new hypothesis. And so the idea that some phenomena may occur much quicker than we normally consider possible should be borne in mind when we're looking at the effects of objects in near-Earth space. Here we have some Greek mysteries. There's the problem, if you like, of the Milky Way, Anaximandros and Democritus. Milky Way, lies in the shadow of the Earth. Well, hardly. Metrodorus and Inopides of Chios. The Milky Way is the former path of the sun. Well, some people think that the Greeks simply lost it as far as astronomy was concerned. They were totally off beam. But if you look at that and you interpret it, if you interpret it in terms of what is the brightest misty patch in the sky, well, that's actually the zodiacal light, and that is in the shadow of the Earth, and it is the path of the sun. So if you were to imagine the zodiacal light being maybe 10 or 100 times brighter than it is now, owing to there being more dust in those days, then you can begin to understand some of these comments. Doesn't mean they're right, but you can begin to understand them, and therefore you don't have to throw them out totally. So I've got a few slides to wrap up with. Maybe I've spoken too long, but near-Earth asteroid impact is unique. It's amongst all risks. The risk is unbounded, and by that I mean that not just civilization, but survival of the species is at stake. And in fact, you could imagine an impact that would wipe off all life on Earth. And as far as we know, life on Earth is the only place in the universe where life exists. So it's quite a significant statement. I'm not saying I believe that, but it's the point that some people have argued. Impacts are predictable, and that's because you can predict their orbits if you observe them far enough in advance. And so you can begin to make plans for an impact, provided you have enough warning. And if you have warning, they are potentially avoidable because a lot of the risk can be mitigated. Whether you choose to is another matter, but you could, for example, remove a population from ground zero if it was a small impact. You could store food supplies, or the rest of it. And of course, if you had enough warning, you could deflect the near-Earth object in space so it never hits the Earth. And then the question is, who controls this high-tech solution? Who controls the deflection technology? Because if you can deflect an object from the Earth, you can certainly deflect one to the Earth. And the smaller the object, the better it is, because it's easier to deflect and it has a more localized impact. And you don't need me to dwell on that, because you can easily see how that could become a weapon. However, assessing the risk, contributing to this uniqueness, presents many difficulties. The impact hazard due to near-Earth objects is a unique conjunction of these difficulties. We don't have any recent claims experience, apart from the historical record. There are these unbounded consequences, so where do you draw the line? Particularly if they're very low frequency. Maybe you say, okay, well, we'll ignore anything that's unlikely to happen within the next 100 or 1,000 years. That's what reinsurance companies tend to do. There's the global reach, which I mentioned before. So who has the responsibility to act? Is it us because we understand it? Is it some other country because they've got the technology? And then who controls it? And then you've got an objective way to rank risks, which is the actuarial or insurance approach. And so if you look at, you just make the analogy with COVID, you see there, suppose we had, make the argument simple, suppose there was 100,000 deaths, each worth £1 million, then that's 100 billion pounds easily. So it puts the amount of money that we're spending on the pandemic into a quasi-sensible perspective. And the risk is unbounded, so it will occur at some point, which can be predicted and can be avoidable. And so makes a lot of sense to keep this NEO risk in the frame, and particularly on the National Risk Register, even though it could be argued that it's laughable compared with all the other things we have to deal with these days. So this gives us, I would argue, a new perspective on our place in space. Through nothing else other than curiosity-driven research, we've discovered, humans that is, we've discovered we live at a special time in the history of life on Earth. We recognize Earth's place in the universe. We recognize that Earth is a bombarded planet. And we recognize that Earth is an open system, a change of mindset as great, if you like, as the one that led Copernicus to displace Earth from the center of the center of the universe, actually. And we also know that impacts hold the key to the long-term survival of a technological civilization, because we're more vulnerable to changes in the environment than our long-term ancestors were, simply because they were out collecting berries and things from the land. And when the environment changed, they were able to migrate, whereas we're not up to that these days with all our technology. And we also know that impacts hold the key to the long-term evolution of life on Earth. So for the first time in the history of life on Earth, 3.8 billion years or so, these facts are known, and a species has evolved, namely humans, with the knowledge to mitigate the impact hazard. And so the question then is, will we be the ones to rise to the challenge, or will we, like the dinosaurs, look down on Earth only and be subject to the next impact when it happens? And Toulmin is a very interesting man. He wrote a book called The Return to Cosmology in the 1950s, I think, maybe 60s. Human beings are the beneficiaries of history. Our fate within this historical scheme depends on our adaptiveness and on the use of our intelligence in dealing with our place in nature. So with that, I think I should stop, and I'm very happy to take any questions. Thank you.
Mark, thank you very much. That was a very knowledgeable talk, very sobering ideas you've put across very well. Thank you for that. Could I ask you to stop sharing your screen, please? Ladies and gentlemen, as always, it's question time. For digital hands first, I have a couple of screens to scroll through. So if you're going to wave at me, assist in waving. So Andy Deavy, welcome, sir. Can you unmute yourself, please?
Yes, thank you. Excellent talk, really enjoyed it. Thank you very much, Mark. My question is, we've got the systems where we're trying to detect the near-Earth approach in asteroids and comets, but there's also where things are actually eating, aren't there? So presumably with all the satellites that grow up there, is anybody collecting a database on the number of actual impact events on the atmosphere and the size of the smaller stuff that's actually getting through on an annual basis?
Thank you, Andrew. Yes, I think that's right. They are collecting that because there are satellites that are looking down on the Earth. As far as I'm aware, they haven't. In fact, perhaps that's how they estimate the size of the smallest impacts. In other words, the size of the objects that span the range of the largest but infrequent fireballs and the objects that can be seen infrequently from space hitting the Earth somewhere. So those spaceborne detector systems are well worth maintaining. But the only question I would make about them, it's not their fault, is that by necessity, we're looking at the Earth, or they're looking at the Earth at a particular moment in time, in other words, now. And as I tried to explain, the effects of comets, and particularly the time evolution of debris trails and so on, does mean that it's very difficult to be sure that those types of observations are applicable to the medium or long term. So you always have to be careful in interpreting the results, but they are doing that, and it's a very valuable database that's gradually being built up, giving us some information on the size distribution of the smaller objects that run into Earth.
The other point is it could potentially be corrupted by space debris that's falling back as well, couldn't it?
Yes, that's right. So when people see a really bright fireball, sometimes people worry whether it was a natural meteoroid running into Earth, or whether it's a fragment of a rocket or something, so, or a satellite even. So you're right, but I think at the moment those impacts that have been recognized from space have been mostly natural phenomena rather than space debris. A lot of the space debris is much smaller in size, although there is raises the interesting question of the runaway, I forget what they call it, sort of avalanche effect in the near-Earth space, where you have the breakdown of, or collisions, fragmentation of large objects, leading to a runaway where you suddenly find the Earth is surrounded by so many small objects which act as projectiles for satellites you'd like to survive, then makes the near-Earth space a very dangerous place for satellites.
Thank you.
Okay, Andy, I'm still looking around for questions. A digital hand would be useful. Oh, Catherine, thank you for using the technology. Catherine, can you unmute yourself, and can we have your question, please? Catherine, can you? Oh, there you go.
Yes, I guess I muted myself. I was watching Anton Petrov, who does a YouTube channel about science and technology. And on the 13th of October, he actually did a talk about some people. I think there's somebody who used to work at Lawrence Livermore National Laboratory, saying that you can actually use nuclear weapons to actually deflect, or it actually makes a noticeable difference if there's an asteroid between about 100 meters and 500 meters coming in, and you can actually mitigate a lot of the problems by firing a nuclear weapon at it, even though it's actually coming in quite late. Have you heard of that?
Yes, that's one of the deflection technologies that people discuss.
Yes,
Another is ballistic technology, where it's not a weapon, but it's I don't know, a fridge or something. Imagine something like a fridge. You just run into it, like they did with Comet. It was Comet Tuttle, I think it was, which they did already. So the technology exists to rendezvous with objects in space, and whether it's a nuclear weapon, which has the highest energy density and therefore likely to produce the greatest movement of the object in its orbit for you, for your the power that you've got available. It's the best, if I can put it in quotes, the best way to deflect a small object, maybe even a big one. And if it was a large object, you try anything possible to deflect it, for sure. My question, and maybe this is for you all to reflect on, because I have my own views, but not everybody will agree, is that the focus on small objects is understandable, because the most likely next impact is going to be a small object, Tunguska size or smaller. And therefore you can understand why people are looking at discovering more and more smaller objects, and also looking into deflection technologies for small objects, because that's the way you will start to learn how to do it with bigger objects and all the rest of it. So it makes, in that sense, there's a rational argument. The difficulty is, as I said at the start, or near the start, that for every asteroid that's on a Earth approaching trajectory, in other words, one that you could that you think might run into Earth at some point, there are probably tens or hundreds or thousands that are on Earth near missing trajectories, and which with the same technology you could deflect onto the Earth. And I would be slightly concerned that some clever person might develop a technology that could accidentally, on purpose, deflect an asteroid onto a city of a group of people they didn't like. So it's an interesting puzzle. At what point is the cure, as it were, worse than the disease that you're trying to cure? And I don't know the answer to that, except that I'm certain that people who talk about nuclear weapons and deflecting small objects must have thought about it. And in fact, we did we played a little game to ourselves in our MAR, my colleagues, David Asher, along with Nigel Holloway. And the idea was, could you deflect an asteroid onto an arbitrary city on Earth from the then known database, which as you know is small compared to what's now known, without anyone finding out? And the answer was yes, in principle. So you would look at an asteroid, you would identify from the catalogue an asteroid that was going to miss Earth, and then it would go round the sun and come out of the daylight sky, and it would collide with your chosen city, because you would have rendezvoused with it, and you'd have nudged it half a dozen or more times with small impacts or small nuclear weapons, if you want. Didn't need to be nuclear necessarily, but small nudges. And just like in golf, you would work out how to sink your golf ball after 10 strokes rather than a hole in one. And we chose Telford. Sorry if anyone knows anyone. But we found we could nudge an object onto Telford without anyone knowing, with perfectly reasonable physics. Of course, we've got no technology to do that yet.
Thank you very much. Thank you.
Next question, please. Jez Robinson, can you unmute yourself, sir?
Howdy. Yeah, I was interested in what your thoughts are on the harvesting of materials from near-Earth asteroids, and do you think, within the next century, that's something we'll be doing a great deal of? Or
I predict, I would say yes. That's my guess. So obviously only a guess. We're running out of raw materials on Earth, not all raw materials, but many of particular kinds. And some asteroids would have masses, quite literally masses of material of the sort that you could potentially use in industry. So I suppose the question is, it turns around to how easy is it to put our energy generation requirements off the surface of the planet? How easy is it to put our industrial technologies needed off the surface of the planet and all the rest of it? And I suppose it would be a foolish person who would say never. That's really all I'm prepared to say, really. I would say that if there's profit in it, then sooner or later someone will find a way of doing it. And I forget his first name, a man called Lewis, who wrote a book on asteroids and mining asteroids. I think it was about 1980 or thereabouts. You could look it up. But he explained the economics and the physics of how you might do this, pointing out that just like the Treasury looks at risk from both a positive and a negative perspective, and let's not be too negative or too dark in our thoughts, these near-Earth objects also have the capacity to be of great benefit to humans, perhaps in the exploration of space, those that carry water in their subsurface layers, and similarly those iron asteroids that carry interesting other materials which can be used. And maybe you'd want to bring them down to Earth with as little negative impact as possible, or maybe you deal with them in space. But that's an interesting way. And if humans continue to do what they're doing, probably that will happen in the distant future.
Yeah, as you said, if we can deflect the energy or control the asteroid's momentum, then we can put it in a stationary orbit around the planet, hopefully one day, I guess, and harvest it that way.
Yeah, and similarly, if you want to use asteroids as a near-Earth asteroids as a jumping-off point to explore the outer parts of the solar system, it might be easier to attach your rocket or whatever to an object as it passes close to Earth, and then you've got a free ride out to the outer solar system.
Thank you.
Okay, thank you, Jez. Mick Nichols. Good evening, Michael. Can you unmute yourself?
Hi. I was just going back to what you were saying about impacts on Earth and mass extinctions. Is it not time to rethink the Drake equation? Because to get to human beings, what we've got on Earth, we've needed 5 mass extinctions. Whether it's been natural causes or an asteroid impact, if any one of them had not happened, you wouldn't get intelligent human beings. The Drake equation doesn't take into effect any mass extinctions at all. I mean, you can't just get an ocean and then get human beings. It don't work like that.
Yeah, you're absolutely right. I'm not sure whether people have tried to include these effects. There are so many uncertainties in the Drake equation. This is the equation where people estimate how many planetary systems are there in the galaxy that might have life forms, and then how long might it take for those life forms to develop into technological civilizations like our own, and all the rest of that. But I think it's a good point you make. It is highly contingent, the process which has led to humans, and evolution isn't always, how can I put it, always moving in an ascending trajectory. You can also evolve backwards, as it were. So I think that the effect of the mass extinctions makes it harder for life forms to develop. It also produces those opportunities for new life forms to move into the ecological niches that have been destroyed. So the way it works is, as I understand it, I'm not an evolutionary biologist by any chance, but as I understand it, if you have an ecosystem, a particular environment, and if nothing major happens to it, then basically the life forms develop towards some kind of quasi-equilibrium. But then if you have an asteroid or a massive climate change or something, then there's going to be changes, and then new life forms evolve to fill the gaps left behind by the others. So it's not obvious that that isn't a positive thing for the development of technological civilizations, but it could well be a bad thing for explaining how particular types of life forms maintain themselves. So in that sense, I think you're making a very good point. There were a few things cropped up on the screen as I was talking, so maybe others have got different views. I didn't really get a chance to read them, sorry.
There was just a discussion about Rolls-Royce engineers developing an atomic engine for space. And the thinking is that it will be used for a mining project.
For a mining project, okay.
Yes.
Okay.
And one of our members is a retired mining engineer. And just the thought that he might want to put a team together, go do it.
Yeah, well, that would be fun. I think
put on his Bruce Willis type vest and get out there.
Well, if I can just make one point, there is a big, how can I put it? There's two schools of thought. One school says that we should explore space just for the point of view of knowledge, and that basically means we develop robot technology and put our machines in space so we can explore very, very hostile environments and learn more about the solar system in that way, and maybe even carry them to distant stars for the same reason. Another school of thought, which you also see happening almost in front of our eyes, is that humankind's destiny lies in space, and that manned space travel is the way to go. And you can see somewhere in between that is this idea of exploiting the resources of space, and to what degree. And so I think we're living through a very interesting time. Whether any one of those, that spectrum of opinion, will end up winning is anybody's guess, and which one it is too.
Mark, thank you for a very entertaining and a very thoughtful evening. Ladies and gentlemen, it just remains for me to ask you to give Mark our usual Mexborough Swinton Astronomical Society. Thank you. Thank you very much, Mark.
Thank you very much. I've enjoyed it. Good night.